6.5 is on page 685 in the book. Talks about physical applications. There are a few applications in there. In our case, we're going to focus on specifically one, which is work. So if we have a variable force, if a variable force moves an object in a positive direction along the x-axis from point A to point B, then the work done on the object would be the integral from A to B of f of x dx, where f of x is the force. So keep in mind, if the force is varying, then as you move an object along from A to B, the force is going to change accordingly, either increase, decrease, depending what you're doing. An integral will sum up all of these different forces and just add them up as all of the different work required at different stages and sums them up. For example, we're going to focus specifically on mass spring. If you have a spring and a mass attached to it, if you pull that spring, actually it doesn't need a mass. It could be with a mass, it could be not without a mass, but that's a spring. So you let the spring rest. We assume that's 0. Now, two things: either you pull the spring or compress the spring. Well, you'll notice if you start pulling the spring, and as it stretches, it's gonna become more resistant. So when you first try pulling the string, let's say the spring looks like that. If you start pulling the spring, you're gonna notice in the beginning it's very easy to drag, but you'll notice between 0 and 1 inches, it's the simplest. From 1 to 2 inches, even though that's still an inch just like that one, this is going to be harder. The resistance is going to be greater. And when you go from 2 to 3 inches, even though that's an inch, that's going to be even harder. The longer the spring stretches, the more resistance it's going to get and the more work it's going to require, because now the force required is varying. That's what they mean by that. And if we're talking about a spring mass system, Hooke's law says the force equal K times X. K is the spring constant. And X is the distance from its resting place. So you let the spring go, and wherever it stops, you assume that's 0. And from that point on, whether you stretch or compress, you count that as X. Now, if we have a constant force, then we really don't need calculus. Simply work is the force times the distance. If you're applying a constant force, something that does not require different forces along the way. But if you have a variable force, then you have to integrate from A to B to accumulate all of these different forces required and therefore get the work. The units for work, if you have kilograms times mass squared per s squared, that's joules. And the units for force, if you have kilograms times mass per s squared, that will be newtons. Now, you really don't have to match the newtons or the joules, the book does. So we start off with the first example. For the following exercises, find the work. Again, that's the only application we're going to focus on. Find the work done when a constant force of 12. So here the force is 12. By the way, just to demonstrate, if you use this when the force is constant, you get the same thing. You will get that. That integral right there will simply give you that force, and dx will give you the distance, and there it is. But if you know it's constant, use the top formula. That's much simpler, like in this problem. Find the work done when a constant force of 12 pounds moves at share from 0.9 to 1.1 feet. So the distance is really 0.2 feet. Work is F times D. Work is the force is 12 times 0.2. I love when it does that. And that makes it 1.2 pound-feet. Now, side note really quick. If you say the work is the integral from 0.9 to 1.1, well, actually that's not 0.9 to 1.1. That is from 0. You went from 0.9 to 1.1 to 0.2. From its resting position to where you dropped it off of 12 dx, well, that would be 12x evaluated from 0 to 0.2. That's 12 times 0.2 minus 0. And again, I'm just demonstrating that you can't get it wrong. If you weren't sure, should I use the integral or should I use just the formula? Well, if you're not sure, use the integral, and if it's constant or not, the integral takes that into account. What is the work done by lifting a child, lifting a 20 kilogram child from the floor to a height of 2 feet? Note that 1 kilogram is equivalent to 9.8 newtons. Well, here again, everything's fixed. It's not changing. So I could use that formula. You could integrate if you want from 0 to 2. That works as well. Work will be, the force will be in this case 20, and 2 meters. Work will be 40, let me see, kilograms. Kilograms meters. And if you want to convert, you could say, well, let's see, kilograms to newtons would be 1 kilogram is 9.8. You don't have to do this. This is a fine answer. But that will be 40 meters, 40, oh, okay, I'll get it right. That will be 40 meters newtons. Okay. And compute the work done for a force. Notice here the force is varying, and it's inversely proportional to the square of the distance. The force is 12 over x squared newtons from 1 to 2. Well, here we're going to say work is the integral from 1 to 2 of 12 divided by x squared dx. That is 12 times the integral from 1 to 2x to the negative 2 dx. That's 12 times, add 1 to the power, divide by that. That's negative 12 into 1 over x evaluated from 1 to 2. Negative 12 into 1 half minus 1. Negative 12 times negative 1 half. And that will be 6. And the units will be, in this case, in newtons, meters. Okay, which is joules. I should just say that. There. Well, I was having such a hard time with that. So keep in mind, newtons is, that's right there. Newtons was kilograms times meters per second squared, and joules was kilograms meters per second squared but the only difference, that's squared. So if you multiply this by meters, pretty much that becomes joules. There it is. The only difference is that's meters squared. So multiply this by meters and you get joules. That's why I was hesitating right there. Wait a minute, meter, yeah. Okay, now spring mass. These here are just regular forces, they're not spring mass. Here you could have integrated from 0.9 to 1.1, that works. But that doesn't work on a spring. You gotta be careful with that. So here, remember, force equal kx. X is the distance of the stretch or the compression, depending on how you're looking at that. But you want the spring to be in its natural length. First, decide how this works. The hard part is figuring out what K is. And keep in mind, if I'm given force, that's the formula. If I'm given work, work equal the integral from A to B of that force. For a spring mass, that's really what it is. The hard part is figuring out what K is. And that's going to be our goal for starters. We try to figure out, okay, how does this work? And let's see how, and they're going to give you both. A 12-inch spring, well, that means, okay, I've been doing that forever. Here we go. The spring length is 12 inches. So at rest, that's what it is. A stretch to 15, we're going from 12. This is 0 to 12. Remember, this is our 0. You know what? I should go by different colors. So 0 to 12 is the original. We want to stretch it to 15. As far as x is concerned, we went from 0 to 3 inches. And that's really what you have to compensate for. Well, first thing you do, you say, well, look, force equal kx. What's the force? By a force of 75 pounds. 75 equal, we're looking for k times 3 inches. So k is 25. So my force for this spring is 25x. So the first thing you figure out, how stiff is the system, then you go from there. What is the spring constant? Oh, we did all of that on the side. So here, I'll just move this up here. And everybody's happy. So the spring constant is 25. If 1 meter, where did mass come from? So again, 1 meter. If a 1 meter spring requires 10 joules to stretch the spring to 1.1, well, if we go to 1.1, then as far as x is concerned, we went from 0 to 0.1. So a 1 meter spring requires 10 joules to stretch. Well, joules would be work. In this case, work is the integral from A to B. And remember, if it's a string mass system, f of x is simply kx dx. Well, it took 10 joules equal the integral from 0 to 0.1 of kx dx. 10 equals kx squared divided by 2 evaluated from 0 to 0.1. Ten equal k divided by 2 into 0.1 squared minus 1. Wait. That should be a 0, right? Okay, that makes more sense. And we're looking at 20 equal k times, this is 1 over 10, 1 over 100. So we would say 2000 equal k. And now I know that the force for this is 2000x. They could ask me anything they want, and I could figure that out what they want. How much work would it take to stretch the spring from 1 to 1.2? Well, that will be the integral from 1. How much work would it take to stretch it from 1 to 1.2? 1, that's 0 to 0.2. And now I know it's 2000 x dx. Well, that will be 2000 x squared over 2 evaluated from 0 to 0.2. That will be 1000 times 0.2 squared minus 0 squared. That's 1000 times, this is 1 over, this is 2 over 10, which is 1/5. And if I square that, 1 over 25, and 25 divides 100, joules. And there it is. Now notice in the first 0.1 meters, it took 10 joules. In the next 0.1, even though equivalent distance, it took 40 joules. As you stretch the spring more, it's going to be more resistant, and the work is going to increase depending on the stiffness of the system. A shock absorbent is compressed. Well, okay, now in this case, we're talking about compressing. Works the same way. It's compressed by 1 inch by a weight of 1 ton. What is the spring constant? Well, F equal kx, and the force is 1 ton, equal k times 1 inch. So k is what? Now, you really don't have to worry about units for k as long as they are using inches and tons. So if they go to feet, then you have to convert, but other than that, that's all there is to it. And that's all for this section.